A two-dimensional square field of size length n is divided by a grid of unit squares. In some of the grid squares there are stones which obstruct the path in the field. A square which does not contain a stone is called a free square. Initially, at some free square, a snake pops its head and starts crawling left, right, up, or down in a straight path. And its path consists of the free squares in our grid. The snake length keeps growing until one of the following two scenarios happens. Either the snake run over itself, as in the illustration. The second scenario is when the snake is getting stuck in one of the ends of the field, or in some stones, and has no room to crawl any further. This brings us to the main question in this challenge. We have the following main problem. Let us assume that the side length n of our field is a power m of 2 plus 1, where m is a positive integer. What is the maximum number of free squares in our field, such that our snake will never be able to run over itself, no matter what the snake's initial point of crawling is, and what path the snake chooses from this point? That is, when our snake stops crawling, it is only because it got stuck between the sides and some of the stones of our field. Equivalently, we can ask what is the minimum possible number of stones, such that the previously mentioned condition is satisfied. Let us check, for example, the case where m is equal to 2, or equivalently, the case where n is equal to 5. Let us distribute 6 stones in our field, as in the illustration. It can be easily seen that with this arrangement of the stones, our snake will never be able to run over itself, no matter what its initial point of crawling. However, if we remove any of the stones in our field, then it can be checked that during its crawling, our snake might run over itself. As we shall see later, the minimum number of stones, to guarantee that the snake will not run over itself, is exactly 6. Let us now check the case where m is equal to 3, or equivalently, the case where n is equal to 9. If we arrange the stones in our field, as in the illustration, then it can be easily checked that our snake cannot run over itself. However, the amount of stones that we are using is not minimal. Since we can remove some of the stones in the field and rearrange the stones that are left. And again, we have an arrangement such that our snake cannot run over itself. However, if we remove any stone from the current arrangement, then it can be checked that our snake can run over itself in some crawlings. Later we will show that the minimum amount of stones that can be used in such a way that the snake will never run over itself is exactly 22. We will now prove that in the general case, where n is equal to a power m of 2 plus 1, the maximum possible number of free squares, such that our snake cannot overrun itself, is exactly 2/3 multiplied by n multiplied by n plus 1 minus 1. Equivalently, the minimum possible number of stones, such that our snake cannot overrun itself, is exactly 1/3 multiplied by n multiplied by n minus 2 plus 1. We will prove our assertion with the following 2 steps. In the first step, we will show that the number of free squares cannot be greater than 2/3 multiplied by n multiplied by n plus 1 minus 1. In the second step, for each n, which has the form as described previously, we will arrange our field so that it will have exactly 2/3 multiplied by n multiplied by n plus 1 minus 1 free squares, and such that our snake will not be able to overrun itself. These two steps together will prove our main result. Let us now prove the first part. For any arrangement of stones in our field, we associate a graph of vertices and edges in the following way. Each free square corresponds to a vertex in our graph, and two vertices are connected by an edge if and only if their corresponding free squares have a common boundary. We denote by V and E, respectively, the number of vertices and edges in our graph. First, we claim that our snake cannot overrun itself if and only if our graph is a forest. That is, our graph is a finite union of trees. Indeed, by definition, a forest is a graph which has no cycles. And it can be easily seen that our snake can overrun itself if and only if there is a cycle in our graph. Since our graph is a forest, it follows immediately that the number of edges is smaller or equal to the number of vertices, minus 1. This is the first inequality that we need in order to prove the first part. The second inequality that we need is that 4v minus c is smaller or equal to 2n multiplied by n plus 1. Let us now prove this inequality. We look again at our graph, in the grid of size, n by n, which divides our field. For each vertex in our graph, we count all the boundary edges around it. Hence, each vertex adds 4 boundary edges. Observe that in this counting, each boundary edge, which corresponds to an edge in our graph, is counted twice. Hence, the total number of boundary edges, which surround our vertices, is exactly 4v minus c. However, this set of edges is a subset of the set of all the edges in our grid, which is of size 2n multiplied by n plus 1. This proves the second inequality. Now we have the following two inequalities. The first inequality is equivalent to the inequality that 3v plus 1 is smaller or equal to 4v minus c. This, together with the second inequality, implies that v is smaller or equal to 2/3 multiplied by n multiplied by n plus 1 minus 1/3. However, since n is equal to a power m of 2 plus 1, it follows that the expression L is an integer. That is, either n or n plus 1 are divisible by 3. Hence, we obtain the sharper inequality that v is smaller or equal to 2/3 multiplied by n multiplied by n plus 1 minus 1. Finally, since the number of vertices v is the number of free squares in our field, our first part is proved. Now, all is left is to prove the second part. That is, for each integer n, which is a power m of 2 plus 1, we need to show that there exists a field with k free squares, such that our snake cannot overrun itself, where k is equal to 2/3 multiplied by n multiplied by n plus 1 minus 1. Equivalently, we need to show that there exists a field with L stones, such that our snake cannot overrun itself, where L is equal to 1/3, multiplied by n, multiplied by n minus 2, plus 1. We will work with the parameter m, instead of n, from here and after. That is, for each positive integer m, the number of stones is equal to 1/3, multiplied by 2 to the power of m, plus 1, multiplied by 2 to the power of m, minus 1, plus 1. Equivalently, the number of stones is equal to 1/3, multiplied by 4 to the power of m, plus 2. To show this, first, when m is equal to 1, we arrange the following 2 stones in our field. Now, at each step, we remove the stone, which is in the bottom left corner. And then, we copy our current arrangement 4 times as in the illustration. Finally, we add a stone in the center, and a stone in the bottom left corner. It can be easily seen that in the arrangement of stones, in each iteration, the snake cannot overrun itself. Also, from our construction, we obtain the following recursion formula for the number of stones after m iterations. The solution to this recursion formula is 1/3, multiplied by 4 to the power of m, plus 2. Hence, the second part is also proved, and hence our proof is finally complete.